Hi, we're going to be solving log equations today. Just a reminder, and one thing that we've talked about in here is trying to be more conceptual and identifying what type of problems we have and what things we know about that problem. So a log equation is one equation containing a variable in a logarithmic expression. Okay, so this one's going to be pretty easy to identify because we'll literally see a log in the equation to be able to make that decision. So when we're solving logs, a really important thing that we're going to end up doing, uh, and we're going to look at this step right here, is making that conversion from a log statement to its corresponding exponential statement. That's essentially how we solve for the variable m, uh, and whatever it is that we're taking the log of. So when we're going through these, the first thing we're going to work to do is get the log term or the log expression by itself. So that way it's just the log, the base, and whatever we're taking the log of. Then we'll make that conversion and then go ahead and solve from there, where we will be dealing with some exponentials. So in general, when we're starting with a log equation, we should think and know that there's got to be an exponential step at some point. And when we get to that exponential step, the x should not be part of the exponent. Okay, the x is going to be what the equation is equal to. So let's jump right into it. Um, Another thing that I want us to think about, again, being more conceptual and identifying things we know about the problem, is the domain of logs are restricted, right? Because of values we can get with exponentials, we're kind of limited with the values we can take of logs of, right? So we can't take logs of zeros or negatives. Now we want to keep that in mind as we work through this problem. And if we get an answer, we just want to check that. Okay, if we plug this answer back in, are we taking a log of a negative or zero? And if so, we have to exclude that value. Okay, so we'll keep that in mind as we work through these. So for part A, I'm noticing that this is log base 4 of x plus 3, meaning that log expression is by itself. So now we can go ahead and make that equal conversion to its exponential. So to do this, I keep the base of the log the same, and I switch the position of the other two terms, making this 4 squared equals x plus 3. Right? That's one of the very first things we did in this log unit. And now from here, it's easy, right? 4 squared is 16 equals x plus 3 minus 3x is 13. And we've come up with our answer. Now, again, we just want to check this and make sure that when we plug it back in, we're not seeing any errors within that domain. So if I plug in 13, 13 plus 3 is 16, and I can definitely take the log of 16. Now, just to further even check our work, log base 4 of 16, remember that if I have log base 4 of 16, really what this equals is 4 to the power of what is 16? It would be 2, right? 4 to the power of 2 is 16. It's exactly what we were trying to get this log equal to in the first place. All right, so that's basically it. But again, we need to get the log term by itself. So here in part B, we have to do something before that. Now, one thing that can be kind of tricky here, because we know some log properties where this coefficient can become the exponent, that actually isn't going to be very beneficial to us. Because if that's the exponent and we make that conversion, it doesn't work out quite as nice. So a better thing to do with this 3 is to actually divide it out, right? This is 3 times the natural log of 2x. So when I divide both sides by 3, we get the natural log of 2x equals 4. Natural log, or ln, remember that is just simply a log with the base e of 2x, which equals 4. Now, you do not need to write this step out. I like to do it when I'm explaining it, just as a reminder that natural log, it's still a log, just like what we saw here in part A, just the base is that specific number of e. And so now we have the log term by itself. I can make the conversion to the exponential form, so e to the power 4 equals 2x. When we're working through these problems, we're going to work to keep our answer exact for as long as possible, meaning I'm not going to figure out what e to the 4th is, because that's going to be some decimal that goes on for forever. So the first thing I'm going to actually do is divide by 2. So e to the power 4 divided by 2 is equal to x. We would consider this answer to be exact. Okay, because no matter how many decimal places we write this for, we're rounding at some point. Okay, so when you're working on your homework and when you're working on these problems, make sure you're reading the question to see how the answer should be evaluate it out, whether it be exact, or a lot of times we end up having to round it, and we round it to typically like 2 decimal places, 2 or 3. So just a reminder to do E, it's the second version of ln. So I'm going to go ahead and hit second ln, and then that'll automatically populate to the exponent, e to the fourth. I can press enter and then divide that by 2. I get 27.299, so if we round to 2 decimal places, we'll round that up and call it 27.3. Okay, and this is our rounded answer. All right, so we're going to go about it this way if there is just simply one log in the equation. Here we can condense and use some of our log properties to condense them down and get the log by itself. We'll use this same idea. You're going to see that there's some different strategies to solve for these logs as well. All right, so here's another good example of just using some of the other things we've done in this unit already. So in order for us to be able to make the conversion from a log statement to its equivalent exponential, we need to have just one single log whose coefficient is 1, right? That's what we were doing. A was already set up that way in the previous problem. B, we had to divide both sides by 3 to make that happen. So it is sometimes necessary to use the properties of logs to condense these logs into a single logarithm. And that's what we're going to do here. Okay, so I'm recognizing that I have 2 logs equal to a number, and I can use some properties to condense these logs together and make it one single log, which I can then convert. Once again, we need to think about our domain. I didn't do a good job of that in part B. It didn't matter there. But we want to think about the domain here at the end. So I'll make sure I don't forget that this time through. So when I have 2 logs that are being added together and we want to condense them down, the base stays the same. And when they're adding, I multiply the 2 parts for what I'm taking the log of. So I have log base 2 of x times x minus 7 equals 3. Let's go ahead and multiply and distribute this x to the x minus 7. So it's x squared minus 7x equals 3. That x squared minus 7x, having the parentheses around it, means they're grouped together, and that's what we're taking the log of, both of those terms. So now we have the log by itself. I can make the conversion to its corresponding exponential. So 2 to the power of 3 equals x squared minus 7x. Now, going along the lines of thinking more about the problem and kind of where we're at and what work we need to do to get x by itself, well, I'm noticing I have an x squared here, which is a quadratic term. Since it's quadratic, I should expect a factor. And more than likely, I'm going to get 2 unique solutions. Those solutions will then have to be checked to make sure that any of those values don't end up in our values we're excluding from the domain. Okay, so first thing, 2 to the power of 3 is 8 equals x squared minus 7x. When I go to factor, if I can leave the a term as a positive, and especially a positive 1, I'm going to do so. So I'm going to minus 8 here and get that 0 equals x squared minus 7x minus 8. Well, this factors, right? Finding 2 numbers that add to negative 8, add to negative 7 and multiply to negative 8. How about x minus 8 and x plus 1? Since a was 1, I didn't need to do any grouping there. And then we factored to be able to take each of those factors and set them equal to 0, where I get x equals 8 and x equals negative 1. So I have 2 solutions here. At least all the work led us to get to these 2 solutions. But like I said, we need to keep in mind the domains of logs. So we need to plug these back in. And it doesn't need to be like a worked out plug back in. Sure, by plugging it in and working it out, we can confirm that this answer is right, checking all of our work. But really the main thing we're going to look for is, are we taking the logs of any negatives here? So when I plug in 8, I have log base 2 of 8. That part's good. And then log base 2 of 8 minus 7, or log base 2 of 1. So that is also good. So 8 seems to be a solution that definitely works. Again, we could work those or evaluate the logs out once we plug in 8 to confirm that it equals 3. When I go to plug in negative 1, though, I get log base 2 of negative 1, which is a problem. I can't take the log of negative 1, no matter what that base is. So in this case, negative 1 is not actually a solution. And we have a name for this type of thing. This is called an extraneous solution. And what that means is all of our work, all of the algebra we took to get to this answer, specifically just 8, led us to also get -1. Okay, but because we went from really, right, there's no x squareds in the original problem, but based on how we solved this problem, we ended up with an x squared, and thus giving us 2 solutions. We're changing basically the degree of the problem, I guess is kind of a good way to think about it. When we change the degree, we're almost gaining an extra solution that doesn't work, which is this extraneous solution. So again, all the algebra got us to this solution, but when we plug it back in, it does not work, and thus it is extraneous. That's not something you typically need to identify. The main thing is just saying that 8 is the only solution, and -1 is not a solution. If you call it extraneous, great, you're making those connections, but you definitely need to catch the fact that that is not a solution that works here. Okay, we've got one last set of problems, and then we're going to just jump into a couple applications here with logs. And so this last problem, if we notice, we'll come back to these steps. Let's look at the problem down here. I've got logs on both sides of the equation. When that happens, it's a lot like if you remember back to the exponentials. If I have 2 to the power of x equals 2 to the power of 3, well, the bases are equal. And when the bases are equal, for me to solve this, I just need to set the exponents equal to each other. So we can essentially do that same thing here, where if I condense these 2 logs together, I'll have a natural log and a natural log on both sides. Those parts are essentially equal. And so we can just set what we're taking the logs of equal to one another. Okay, and that's what this is showing. So if we have a log equal to another log, where the coefficients are 1 as well, we can use the one-to-one property. Okay, that's not something you need to know, but you'll see that written in directions sometimes, to then essentially drop the logs and just set where we're taking the logs of equal to one another. Okay, so the exact thing I was just describing. Once again, we'll just make sure that all of our values are greater when we plug them back in, that we're not taking logs of any negatives or 0. Okay, so first things first is to condense the logs just like we did on the previous example. When we're subtracting, that turns into division. So this is natural log of x plus 2 divided by 4x plus 3. And it equals the natural log of 1 over x. Well, these natural logs are equal, and now we can go ahead and drop them, okay, and just set where we're taking logs of equal to each other. Know that this cannot happen until we have one single log equal to one other single log. Okay, it's common for students just to drop the natural logs right from the start, but we can't do that until they're condensed down. Okay, so now I have x plus 2 equals 4x plus 3 equals 1 over x. So we got to solve this rational equation. Well, there's lots of ways of how we can approach solving this. One thing that I'm going to do is just group together all the numerators and denominators. And this is actually where you would hear cross multiplying being applied. Cross multiplying is us just getting rid of the division in one step. So right, this left side is x plus 2 divided by 4x plus 3. And so I can multiply both sides by 4x plus 3. That gets rid of this division. And now the 4x plus 3 is getting multiplied by 1 in that right fraction. Now, the cross multiplying, again, means that we do this all in one step. So I can also get rid of this 1 divided by x by multiplying by x to both sides. And when I multiply by x, that gets rid of the dividing by x. And so this left side is x times x plus 2, which is x squared plus 2x. And it equals 1 times 4x plus 3, which is 4x plus 3. And now we're on our way. Once again, this is a quadratic equation because of this x squared showing up. I want to leave this a value as 1, so I'm going to subtract these terms over to the left side, making it x squared minus 2x minus 3, which equals 0. This factors to be x minus 3 and x plus 1, giving me solutions of 3 and -1. Now, once again, we just need to plug these back in and make sure that we're not taking logs of 0 or negatives. When I plug in 3, 3 plus 2 is 5. That works. 4 times 3 is 12, plus 3 is 15. I can take the log of 15. 1 over 3, I can take the natural log of 1 over 3. But now when I plug in -1, it works here, right? -1 plus 2 is 1. That one's okay. 4 times -1 plus 3 is negative. So that's a problem, meaning we cannot use -1 as a solution because we're excluding that from the domain. So -1 is our extraneous solution in this example. Now, I don't want us just to assume that when we get a negative answer, that's the one that's extraneous. It all depends on the specific problem. So make sure that after we get our answers, we're plugging them in, whether you get just one solution like we saw in the first two examples, or whether we get, especially if we get to like what we've seen in these past couple examples here. Okay, we're just going to go ahead and use these solving tools that we just went over to now go ahead and solve a couple applications. All right, so it says, alcohol and risk of a car accident. Medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. The risk is modeled by the equation. It's always nice when we're provided an equation, where X is the blood alcohol concentration. I like to identify these variables. That's the blood alcohol concentration. And R, given as a percent, okay, that part's really important as you're reading this problem, meaning we're not going to convert the percent to a decimal. R is the risk, or the percent risk of having a car accident. What blood alcohol concentration corresponds to a 17% risk? Okay, so that's our R, right? That percent written as a percent of a car accident. So we're solving for X, right? X is the blood alcohol concentration. That's what the problem is asking for. So I'm going to go ahead and plug 17% in for R, and as a percent, so 17 equals 6, e to the 12.77x. Well, again, one thing that I've been wanting us to work on is think about what type of problem are we seeing. This is an exponential, which we didn't go through the exponential problems in this video, but something we have covered. When I'm starting as an exponential, I should assume that there's going to be a log step somewhere along the process. And in order for that log step to happen, we need to get the exponential term by itself. So I'm going to first divide by 6 to get 17/6 equals e to 12.77x. And now that I have this by itself, this is where we can do one of two things. We can just convert it over to its corresponding log statement. More commonly, we're just going to take the log of both sides. And actually, let's take the natural log of both sides, right, with that base of e. So natural log of 17/6 equals natural log of e 12.77x. Now, I'm just going to go through all the steps here, even though this is an equation that we've covered, just so that we're kind of reminded as to how this plays out. So when we're taking a natural log of something that has an exponent, that exponent can become the coefficient. So now we have natural log of 17/6 equals 12.77x natural log of e. Well, this 12.77x natural log of e, all those things are being multiplied. 12.77 times x times natural log of e. Natural log of e, that is just equal to 1. Okay, that's a property that we should have down, right? That's log base e of e. And so now, the only thing I need to do to get x by itself is divide both sides by 12.77. And this is our value of x, which is completely exact, right? I haven't typed anything into my calculator yet. And that's important that we do that until the very end. And now I can go ahead and grab my calculator and see what this equals. When I do this, I'm going to make sure, in fact, I'm just going to do the natural log of 17/6 first and press enter, and then divide that by 12.77. Not 0. There we go. And does it tell us where to round it to? Well, let's think about what this is. X is the blood alcohol concentration. Okay, that actually ends up being a percent. So it might make sense. Let's round it to 3 decimal places. We'll call this 0.082. And so this would be the blood alcohol concentration. You could also say that it's about 8.2%, corresponds to a 17% risk of having a car accident. Okay, so again, we have our answer in exact terms. Because it's dealing with this application, this is going to be the better answer and one that your Math Excel assignment will like a little bit better. Okay, so all that is just us using some of the equations and solving tools that we've gone through already and applying it to more application. And we're going to do this one more time. Now revisiting the compound interest formulas. Remember, this is how like investments work or loans or something along these lines. So this can be a really useful way to make some decisions. So we are given the compound interest formula for compounding n times. It says it describes the accumulated value A of the sum of money P. We already know these variables, so that's not new. T years at an annual percentage rate in decimal form compounded n times year. How long will it take $25,000 to grow to $500,000 at 9% annual interest compounded monthly? Okay, so we have almost every variable here. When it asks for how long, that means I'm solving for t here. Okay, so let's set up what we know and then work to solve it from here. So we're trying to figure out 25,000 is our principal, meaning 500,000 is the amount we're trying to figure out when we're going to get there. It's 25,000, and then 1 plus, this is 0.09 divided by n, which n is 12, to the power of 12t. And that's what we don't know, right? That's what we got to figure out here. So the trick for this is going to be leaving this exact as possible for as long as possible. And it's going to take some really good calculator work. So a lot of us might want to do this 0.09 divided by 12, and I get 0.0075. That actually is an okay decimal. That's not rounded. That is exact. So to make it easier, we absolutely could write this as 1 plus 0.0075. In fact, that would make it really easy. But there might be times that you get like 0.03 divided by 4. Wow, that ended up being the same thing. That wasn't a good example, Mr. Youngren. How about 0.03 divided by 3? That's not a good example either. Okay, the point I'm trying to make is sometimes a decimal might go on for forever, and even if we write them all down, it might be rounded. So I'm just going to leave this as is for as long as I possibly can. So the first thing is, just like before, we need to get this exponential term by itself. Okay, so a lot like what we did on the last example. So I need to divide by 25,000. So 50,000 or 500,000 divided by 25,000 is 20. And that equals this 1 plus 0.09 divided by 12 to the power of 12t. So now I'm going to go ahead and recognize, one, that the exponential term is by itself. So take the log of both sides. So log of 20 equals log of 1 plus 0.09 divided by 12 to the power of 12t. And all I'm going to do is leave this exact until I can get t by itself. So 12t can move down to the coefficient. So log of 20 equals 12t log of 1 plus 0.09 divided by 12. And again, this is all just multiplication, 12 times t times the log. So to get t by itself, I need to divide both sides by everything we're multiplying. So divide by 12 and the log of the 1 plus 0.09 divided by 12. So our exact value here is log of 20 divided by 12 times the log of 1 plus 0.09 divided by 12. And this is what I'm going to type into the calculator. Now, a couple things that I'm going to do just to keep everything grouped together. Parentheses around the top are a good idea. They're not necessarily, but a good idea. But we definitely need parentheses around this whole denominator. That way we don't divide log 20 by just 12, and then the calculator might think to multiply by this log. So the parentheses around the whole numerator and denominator can be really helpful. So log 20, and since that opened a parenthesis for the log itself, I need to close another one for the whole numerator, and then divide it by open parenthesis 12, and then I can just go straight to the log. 1 plus 0.09 divided by 12. Close the parenthesis on the log, and then close the parenthesis on the denominator, and we get t to be 33.4 years. Okay, it doesn't tell us how to round, so we'll just round to the nearest tenth. And that's about how long it would take. Okay, so 25,000 to grow to 500,000, 33.4 years for doing nothing. That's pretty good. Okay, that's a good investment, right? Guaranteed money over the course of time. Okay, well that does it for this lesson. You have a Math Excel to follow. Have a great rest of your day.